So this question not only asks us to figure out the angular momentum of a single particle, but now we have to figure out the angular momentum for two particles and figure out how to combine them. So let's start by considering the angular momentum of the blue particle. To do this, we're going to need to know its linear momentum, which is its mass times its velocity. The direction of its velocity points to the right, and I know the mass and its speed. So this has a linear momentum of 50 kilograms times 2 meters per second, or 100 kilogram meters per second. And it's directed to the right. But to get angular momentum, we also need to know, first of all, about which point we're calculating the angular momentum. In this case, it's this pink point here. So we need to know the r vector, but in this case, just like it's in the last case, what we really care about is r perpendicular, which I can see is this blue arrow here. And the magnitude of r perpendicular, based on the context of the problem, is half this distance here. So it's 1.5 meters. If I take the momentum and I multiply it by r perpendicular, I'm going to get 150 kilogram meters squared per second. So now we want to also figure out the angular momentum of the green particle, which has the same mass and speed, but it's moving in the opposite direction. So I can still get the same magnitude for its momentum. It's just going to be directed to the left instead of to the right. And then for our r perpendicular, that also has the same magnitude. It's 1.5 meters. So the magnitude of the green particle's angular momentum is also going to be 150 kilogram meters squared per second. So what you might think is, since these two particles have opposite linear momentums, same magnitude, opposite direction, so the net linear momentum of this system would be 0, you might think that might also be true for the angular momentum. So a tempting answer here might be A, that these two angular momentums cancel. But that would only happen if the angular momentums also pointed in the opposite directions. And to do that, we need to do r cross p for each particle. So for the blue particle, we've already calculated its magnitude, but now we need to think about its direction. R goes from the pink dot up to where the blue particle points, and then I need to turn my hand so that my fingers curl towards P, which means my thumb is pointing into the page and my fingers are curling clockwise. So the blue particle has clockwise angular momentum about this point, which if I picture how it's moving, that kind of makes sense. In a sense, it's like rotating in the clockwise direction about this pink point, even though it's just translating in a straight line. Now I'm going to do the same thing for the green particle, which is moving to the left. So its p vector changed directions, but its r vector also changed directions. So r is going down and to the right, and if I curl my hands towards p, that also gives me an angular momentum vector that points into the page, or again, a clockwise angular momentum vector. So same magnitude, same direction. These two vectors are going to add their magnitudes to give us answer D of 300 kilogram meters squared per second. All right, so now that we've gotten used to calculating angular momentums and their total magnitude and direction for a system of particles, what we want to think about is the fact that angular momentum is one of these conserved quantities means it's useful to think about when the angular momentum of a system is constant. So just like we did for energy, we looked at the work energy theorem and said, when is the energy of a system going to stay constant? We did the same thing with linear momentum. We said, when will the linear momentums of a system stay constant? And now we're going to ask ourselves, when will the angular momentum of a system stay constant? And so the simplest way to get this is if you have an axis about which you're calculating the angular momentum, if the sum of the torques is exactly 0 about this axis, then the angular momentum has to be constant here. So if we have a net torque of 0, then we don't have any impulse due to torques, then we can't have the angular momentum of our system change. That's what the impulse momentum theorem says, is that, or the angular impulse momentum theorem says, is that if you have an angular impulse due to torques, that's going to change the angular momentum of your system. But it's also useful to think about, when will we just have the angular momentum of the system being approximately constant. And one way to do this is if you keep the time interval short enough such that the external torques, which are not too large, don't have enough time to appreciably change the angular momentum of the system, then you can get that the angular momentum of the system is approximately constant, or that delta L is approximately 0. Why are we making a big deal about this? This seems kind of hand-wavy, but notice that this worked out really well when we were talking about linear momentum for collisions, that if we made our system both colliding objects and we made the time interval short enough, then we could sort of say that the impulse due to these external forces was sufficiently small that we could just talk about angular momentum staying constant for that short time interval right before the collision and right after the collision. With angular momentum, these collisions are going to look a little bit different. And again, with linear momentum, we talked about collisions being more of an interaction. Same thing here with angular collisions. So one type of angular collision or interaction we're going to think about is, say you have an object, like say it's Einstein, and it's spinning on something that it's a pretty good spinning surface. It's got some nice ball bearings. It has negligible torque from friction. So we can say that the angular momentum of this object won't appreciably change as long as we make our time interval short enough. So if I don't have a platform like the one shown in this, we have it on campus, but due to COVID, I'm not on campus right now, but I do have a nice spinny chair. If I make my time interval short enough and I spin myself in the chair, over a short period of time, my angular momentum doesn't change until I put my feet on the ground and apply a torque due to external forces. So one thing that this picture is trying to show is that we can also have some fun things happen if we redistribute the mass of our system in such a way that we're not bringing in external torques. There's not external torques that are adding or subtracting angular momentum from our system, but instead we still see some cool things happen here. So if I were Einstein and I had some weights, which I don't, so instead I have these pasta sauces and I hold them out to the side and I get myself started spinning, what's going to happen when I pull my arms in? So let's do the experiment to see if you have a spinning chair and any two heavy-ish objects at home. You can try this at home. So I'm going to get myself spinning here, and then I'm going to pull my hands in and pull them out again. And I got a little bit of friction there torque due to friction. I'm going to try this one more time. So I'm spinning, and I pull them in, and that didn't work at all. So I'm going to stop the video.